going to start now by introducing the first talk. The first talk this afternoon will be by Dominic Sulway, PhD student from the University of Bristol, and the talk is entitled Engineering Ultra-Low Loss Silicon Quantum Photonics in the Mid-Infrared. Go ahead.
Okay. Let's just get this going. Okay, all good? Great. Okay, well, hello. Thank you for having me at BQIT this year. I know it's been a challenge to move everything online, but it's been fantastic so far, and I've thoroughly enjoyed it. And thank you for everyone for attending this talk. So I'm Dominic Sulway, and today I'm going to talk to you about engineering ultra-low loss silicon quantum photonics in the mid-infrared. This work was done in collaboration with the list of collaborators you can see here. Lawrence and Josh, I work very closely with the University of Bristol. Yuya and Takayoki, I work with from Waseda University. Quinn has been working with me on a project, and John Rarity is my primary supervisor. So to get started, integrated photonic quantum technologies. Over the last few days, we've seen some fantastic talks on integrated photonic quantum technologies. And all of them, as a sort of zeroth step, require basic quanta. And in photonic quantum technologies, these are heralded separable single photons from spontaneous four-wave mixing when we're generating our photons on chip. These single photon resource states are utilized in all three areas of the quantum technologies: computation, sensing metrology, and communications. To truly enable these applications, the generation of this fundamental single photon resource state is crucial. And it turns out that in quantum technologies, the major limiting factor to the system performance of this component is loss. So there's lots of engineering to be done. So if we were to think of what a heralded single photon source might look like, it might look something a little bit like this image we have here. We've got a pulsed pump being coupled in onto the chip via hopefully some low loss optical interface. We've got a photon pair source, which in this instance for simplicity is a ring resonator. We've got some signal and idler demultiplexing, and we'll talk a little bit more about the intricacies of spontaneous forward mixing momentarily. And then what happens then is we send one of our photons to an SNSPD, which generates an electrical signal, which then is used to turn on a switch. And if these electronics are fast enough and this delay line is low loss enough, then we can turn on this switch in time for this photon to arrive here, and we can route it off to do some useful or perform some useful applications in quantum technologies. Now, crucially, loss in any one of these components is unacceptable and represents a loss of resource for photonic quantum technologies. So the key system requirements. We've got single photon sources. We want them to be bright, pure, high heralding efficiency, and low nonlinear loss. The optical interface ideally needs to be low loss, broadband, application dependent, and scalable. And filters, we need to get pump suppression down to the single photon level, and we'd like for them to have low insertion loss as well, so we're not losing our single photons in the filtering process. And this talk today will be concentrating mainly on these three components. But alongside that, then you need a delay line with low linear propagation loss, a fast low insertion loss, low driving voltage optical switch, and fast cryogenic or possibly cryogenic operation electronics. So, as we said earlier, we're generating our single photons in silicon, and this is using a parametric Chi3 process known as spontaneous forward mixing. We can see this in the diagram on the right by here, where we have two, in the general case, we have two pump photons that generate, that scatter via the mediation of virtual energy levels in the crystal lattice, a signal photon and an idler photon. Now, alongside this nonlinear process, nonlinear absorption can occur as well. So in 1550, column wavelength for silicon photonics over the last 10 years, two 1550 photons have sufficient energy to span the silicon band gap. And so this results in absorption, a non-parametric process exciting free carriers. However, if we move to a slightly longer wavelength, around about 2.1 microns, we get much less TPA because we have insufficient energy to excite electrons across this band gap. And this is just a diagrammatic summary of these nonlinear optical processes. We've got spontaneous forward mixing on the top, and then we've got these these processes that detriment the key performing factors of single photon sources. The TPA will limit brightness, and cross TPA between a pump photon and a signal idler will limit heralding efficiency of your single photon source. So as sort of like ground zero, work done predominantly by Lawrence Rosenfeld and Joshua Silverstone, and where I started my PhD was trying to generate single photons, correlated single photons from spontaneous four-wave mixing in silicon in the TE0 mode at 2 micron. And we did this. We generated correlated photon pairs. We showed that the TPA coefficient, you can see here, is reduced compared to values at 1550. We get a complementary resonance in the nonlinear refractive index, which is crucial for the efficiency of spontaneous four-wave mixing. We get reduced Rayleigh scattering with a 1 over lambda to the 4 scaling. And because we're guiding modes that are slightly larger, we have larger feature sizes. And so this doesn't put as much strain on fabrication processes like electron beam lithography. We're comfortably above the minimum feature size of those lithographic processes. But this was all done in 340 nanometer silicon on insulator platform, where the silicon waveguide is 340 nanometers thick. So what we would like to be able to do is to generate photons in 220 nanometer thick silicon in the mid-IR. The mid-IR, because we get less nonlinear absorption, nonlinear absorption. And because the 220 nanometer platform is much more widely commercially available. So it allows for a rapid development of the 2 micron integrated photonics toolbox. However, there is a problem. So in the previous work at 340 silicon, in the TE0 mode, we were operating up here in the group velocity dispersion regime. And as you can see, group velocity dispersion is anomalous, and it turns out this is a key key prerequisite for generating single photons from spontaneous four-wave mixing. We can see that if we were to operate in the TE0 mode at 220 nanometers, we would be in normal group velocity dispersion regime. And so the phase matching efficiency of our process would be much lower. However, in 220 nanometer thick silicon, we can achieve anomalous group velocity dispersion by pumping in the TE1 mode. And for this, we chose a waveguide width of 1.25 microns. And just to illustrate this, we can see here we've got a phase matching profile dictated by these equations up here. This is for the T0 mode on a 1.25 micron wide waveguide. We've got normal dispersion, and the phase matching efficiency is sort of truncated at quite low signal photon detunings and hugs for small signal photon detunings. Whereas when we are in the anomalous group velocity dispersion regime in the T1 mode, the phase matching bandwidth is much broader, which is good. So we described how we're going to generate single photons, but how do we actually get into the TE1 mode? The way we do this is we inject light into the chips via grating couplers, and these are very good, reliable components in our toolbox that couple the TE0 mode. So we wanted to design an integrated mode converter, and you can do this by carefully designing an asymmetric evanescent coupler. So analogous to the symmetric couplers that are used as arbitrary beam splitters in silicon photonics, where you can split off arbitrary amounts of TE0 light by having symmetric waveguides, by tuning the coupling length and the coupling gap. We can actually convert in the T1 from the T0 into the T1 mode by introducing this asymmetry in the coupling region. And so this is how you design one of these components. To ensure complete power transfer over across the crossover length, we need to essentially phase match the TE0 mode in its waveguide on the top and the TE1 mode propagating in the waveguide in its respective waveguide. And we can see that, and this is done by effective index matching. And we can see that for TE0 waveguide width of 620 nanometers and a TE1 waveguide width of 1.3 microns, we can achieve an effective index of 2.1 in both cases. And this is what these modes look like from FDE simulations in the uncoupled case. And then you can move towards trying to couple these modes by bringing the waveguides very close together. This induces supermodes, which are just linear combinations of the unperturbed modes. And via more FDE analysis and by moving these waveguides closer and further apart from each other, we can calculate the coupling coefficient as a function of coupler gap. And from this equation down in the bottom, we can actually calculate the coupling length for a specified gap. And we want to make these devices manufacturable. So in this case, we've chosen a coupler gap of 300 nanometers, which corresponds to a coupler length of about 35 microns. And then finally, we can verify using 3D FDTD. And so here we can see a normalized intensity plot of an asymmetric evanescent coupler. We can see the waveguide here for the T0 mode is thinner than the waveguide here for the T1 mode. We've got some T0 input. This is coming in, coupling across the evanescent region, and then we've got almost complete transfer into the T1 output mode. And this is simulated to have an extinction ratio of 17 dB and 0.07 insertion loss. And so this is what a experimental setup for a quantum photonics experiment looks like in the mid-IR. The key point here is that on the conversation of loss, we have to clean our pump using bulk monochromators. And then we also have to perform pump suppression filtering on signal idler channels using bulk monochromators as well. We just don't have the integrated component toolbox yet to be able to do this on the same chip as the photon pair generation. And these are very lossy. Full-edge grating couplers in the mid-IR and 220 soy are also quite lossy. But we do benefit from relatively high operating efficiency mid-IR, bespoke mid-IR SNSPDs operating around about 45% efficiency. And so just as a pre-point, we measured the AEC to have 20 dB of T0 extinction, which is similar to what was simulated in the previous slide. And so here's the results. We've actually managed to generate some TE1 photons on silicon with 220 nanometer thickness in the mid-IR. And we can see this here from this, this coincidence histogram. And we can see here that the coincidence rate is scaling quadratically with the pump power, which is the sort of behavior you would expect to see from spontaneous forward mixing. We measured a max CAR of about 8.59 at 0.74 watt peak power, an on-chip per pulse generation efficiency of 3.3 megahertz per watt square peak power. But in order for this to be a real world sort of deployable heralded single photon source, we need to be able to engineer the componentry around it to make sure that we can actually get these single photons that we're generating off chip, and so that we can go and use them for useful quantum technologies. So as an intermediate and sort of analogous way of looking at heralded single photon sources to the first slide, we can have this sort of modular design. And this modular design sort of inspires the need for low loss optical interfaces in the near term. It's also critical because at the moment, most SNSPDs are off chip, stored in cryostats, whilst the chips are in the lab at room temperature. And so to reduce the loss in single photon channels, we really want to be able to get a low loss I/O between chips and detectors. And then in the far term, you can possibly think about having your passives on one chip, where you've got your single photon, your photon pair sources and your filters. Your delay line is in fiber because you're coming off chip anyway, so you may as well do the delay line in fiber. And then we can go to what would be like an actives chip, where we'd have our electronics, our possibly doped optical switch. So in collaboration with Yuya Yonezu up here and Takaya Aoki of Waseda University, they designed this a bespoke adiabatically conic tapered fiber for this project. Conventionally mounted, the fibers have tapering lengths of the order of centimeters. This fiber in particular has a final taper radii of 500 nanometers, taper length of 7.1 millimeters, and it was made with custom SM2000 mid-IR fiber for lower propagation loss. And this comparatively small tapering length actually permits ease of mounting and coupling for prototyping experiments. And so, in terms of designing the on-chip nanotapered silicon nanowire, as it were, to ensure complete coupling efficiency from the T0 mode into solely the T0 mode of the waveguide structure, we need to ensure that we adiabatically taper our on-chip taper to make sure that we're not coupling into radiation modes or higher order modes, just to ensure that highest possible coupling efficiency. And this is done by engineering this effective index anti-crossing here between the supermodes. And we can see up here this transmission into the T0 mode remains relatively consistent at around about 98%. However, crucially, the buried oxide beneath the nanotaper needs to be removed. Otherwise, we get parasitic coupling into the buried oxide layer of our silicon chip, which is what we don't want. We want all of our light going into our waveguide. And so the adiabaticity criterion can be interpreted via these equations here, where the length of the coupler needs to be much, much longer than the beat length between the modes, supported by the waveguide and the fiber. And then we can engineer a coupling length such that we ensure complete power transfer into the T0 mode of the waveguide from the T0 mode of the fiber. And this can be seen in these diagrams by here. This was verified, and our final design parameters for a fiber radii of 500 nanometers corresponded to a start width of 650 nanometers for our taper, tapering down to 200 nanometers over a coupler length of 25 microns, operating at 2070 nanometers in the mid-IR. So here's a nice little concept diagram for what the actual structure might look like. We said before we needed to selectively remove the box to avoid parasitic coupling, and this is what this region here is showing. The silicon waveguides are in this dark charcoal color, whereas the fiber itself is in the white color by here. The tethers here have been attached to the end of the waveguide to ensure that the waveguides remain suspended after the wet silicon hydrofluoric acid wet etch. And the islands by here are to promote a sharper transition from the area that has been etched away by the hydrofluoric acid to the area where we still want buried oxide underneath our waveguide to support it. And so this is what the process flow and device design looks like. We start off with silicon on insulator, we mask it up, expose using via e-beam lithography, etch our silicon waveguides, and this is sort of the midpoint here where we have fully etched 220 nanometer silicon waveguides on insulator. Then we do a second mask spin. We expose again with e-beam in the region where we want to remove that mask so that the hydrofluoric acid can get down in between the mask and the silicon and expose the silicon dioxide beneath. And then after development, we end up with suspended structures that we're going to be using to bring into contact with our silicon, with our fiber, and supported structures for the islands. And for this experiment, we decided to go with what we thought at the time was the simplest design, which is essentially a nanotapered fiber coupler here, a ring resonator for coupling verification. It's going to overlay an FSR on top of our transmission spectra, so we know we're coupling into the chip waveguide. And then we've got a Sagnac mirror up here after a 1x2 MMI just to route the signal back around, and so we can launch and collect on the same fiber for ease of coupling. And this is what the finished fabrication looked like. We can see here that we've got these silicon islands. We've got our tethers coming in to support our waveguide, and then we've got these islands to promote a sharp transition from the region that has been etched and the region that isn't etched. And we can see here that the silicon nanowire is still suspended. And then this is just an SEM of the actual ring resonator for coupling verification and the Sagnac loop to route the signal back through the same fiber that we launched with. So the SEM confirmation of the nanowire survival post-etch, it was a good device yield across 3 chips. We saw between 60 and 70% yield on these nanotapered fiber couplers still being suspended off the box. And the waveguide widths and coupler gaps are consistent with the design that we proposed in our GDS. Obviously, what you put on a GDS and what you get out of an e-beam sometimes is not exactly the same. And so in the experimental setup, we've got a tunable laser source with some polarization control onto a 50-50 fiber beam splitter. We're routing in our light onto our chip as discussed earlier. And then in back reflection, so we've got a tap here to monitor the power going into the chip. And then we've got a tap in back reflection to monitor the coupling efficiency of the chip. And our tunable laser source is 1.98 to 2.09 microns. And obviously the signal we detect here is going to be less 3 dB because we're passively splitting on a fiber beam splitter. And this is what the transmission spectrum looks like. So we can see here a few key points. We've got FSR of around about 10 nanometers, which agrees well with the theory for what the FSR of the ring that we designed should be. We've got a max coupling efficiency of around minus 0.4 dB per coupler. And we've also actually got some Fabry-Perot, we think, overlaid on this. The period of which is around about 87 nanometers, which corresponds to a cavity length of about 7 microns. And we think this is actually coming from cavity effects in the tethers supporting the nanotapered waveguide. And also there's a very large error associated with this. So in the future, we have some simpler, even simpler designs that we hope are going to mitigate this error on this final value. In fact, they were due to be fabricated a month ago, but with the world in the current state that it is in, that has had to be put on hold. So in conclusion, in the first instance, we confirmed that by moving to longer wavelengths, we can curtail TPA and enhance the intrinsic useful nonlinearity of silicon for single photon sources. We've generated single photons on 220 nanometer silicon in the TE1 mode at 2 micron, which enables 220 nanometer silicon insulator for, as a mid-IR quantum photonics platform. And we've demonstrated ultra-low loss broadband optical I/O in the mid-IR. And this is a key technology that will enable the modular testbed for low-loss heralded SPS in the future. The next step, if you ask the right questions after this talk, I might show you some slides, is the design and development of waveguide pump projection filtering and novel solutions for pump scatter rejection in the substrate layers of the silicon insulator platform. So with that, I think that's the presentation done. Thank you for listening, and please feel free to ask me any questions. These slides will be put up on the Slack, and I'll also be answering questions there as well. So thank you.
Thank you, Dom. Some questions are coming in already, but I'll take my chair privilege and ask the first one.
Okay.
So on the 12th slide, the mode conversion does not seem to be 100% efficient. Do you have the exact value of what's the efficiency of that mode conversion?
Yeah, sure. So if we go all the way back, oh, I've gone back too far. Oh, no, this is just gonna, right, okay. Sorry about this.
Soon.
Okay, there we go. This slide here, is it? Okay, yeah. So what's going on here is, we think, is, you're right, there's some T0 on the output. And so 98% is getting converted into the TE1, and then there's about 2% remaining in the T0 waveguide output. Now, the reason for that, personally, I think, is that obviously this coupler gap was determined from FDE analysis, 2D FDE analysis in commercial software package. The accuracy of which in determining the effective indices of the supermodes that dictate the coupler gap is actually higher than how the effective indices are calculated in FDTD. So based off that, I think, I mean, the measured extinction was higher than the simulated extinction. And the effective indices of these supermodes depend on a critical dimension of the coupler gap, which is of the order of nanometers or hundreds of nanometers. The variation in fabrication processes routinely quoted at probably 20 nanometers plus minus in waveguide width. So I think it just essentially all comes out in the wash. You got a little bit of inaccuracy in how the FDTD is calculating the effective indices, but then possibly compensated by the fact that the fabrication process is going to swing you back the other way because of the tolerances on the waveguide widths. It'll
be interesting to see exactly how much that error in fabrication leads to, you know, lack of precision in that mode conversion efficiency. Okay, let me start. There's quite a few questions now, quite a few. The first one, or the top voted one, is from Alex Clark, and it reads: is anything known about the operation of these silicon nonlinear photon sources at low temperatures in the mid-IR, which would be for full integration?
Okay, so in particularly in the mid-IR, there was a recent paper published in the near-IR examining the efficiencies of single photon sources, conventional 1550 wavelengths. And they actually saw an increase in the useful nonlinearity N2 and a reduction in the parasitic TPA coefficient by moving to lower temperatures. And this is all to do with how the temperature affects the band gap of the material at lower temperatures. And so in the paper in Lawrence's paper, we still measured TPA coefficient because we were conducting our experiments at room temperature. And so there is still the wavelengths that we're working at, 2070 nanometers pump wavelength. At room temperature, there's still a TPA coefficient. However, moving to cryogenic temperatures, blue shifts the band gap. And so we would expect in the mid-IR that the TPA coefficient would be completely removed at cryogenic temperatures for the wavelengths that we're working at.
Okay, thank you. There's time only for one more question, and that one is going to be from you and Alan. Great talk, Dom. Are the extra fab processors you need for suspended waveguides compatible with commercial foundry processors? Could it be done in post-processing? Okay, yeah, that's a great question. So if I just grab you, I'll talk while I'm going. Oh, I can't, there we go. Okay, yeah, so actually quite a few commercial foundries now are starting to offer processes where you can have a selective box etch underneath the waveguide structure. So I think ANT, I saw a few months ago, are actually offering this process. So instead of having to, so all of these chips, for the nanotaper fiber project were manufactured in-house with QPIC assets, the electron beam lithography system in Bristol University. And so I think there will become a time where if this takes off, and maybe if we can start packaging this technology appropriately in a scalable manner, that you can just submit these designs to a foundry and just get them to do the entire stack for you. They'll give you your full etch silicon waveguides, strip waveguides, rib waveguides, and then they'll do the box removal for you as well. Yeah, it's something that's starting to be offered by commercial photonic integrated circuit companies. Thank you.